Testing, can you hear me? Testing, can you hear me? Testing again, can you hear me? Alright, this video is public now, so I'm going to be reading about sorry, yeah, I'm going to be learning computer architecture again. And I'm going to be reading from where I last left off. Last time I learned about division. I was learning about division right here. This time I will be learning about floating points. Okay. Floating point addition and subtraction. Problems of floating point addition and subtraction are actually different phases of the same problem. AB can be interpreted in two ways. We can say that we are subtracting B from A, or we can say that we are adding minus B to A. Hence, instead of looking at subtraction separately, let us look at it as a special case of addition. We shall first look at the problem of adding two numbers with the same sign. Okay, before going further, let us quickly recapitulate our knowledge of floating point numbers. The problem is to add two floating point numbers A and B with the same sign. We want to compute a new floating point number. In this case, the sign of the result is known in advance. All of our subsequent discussions assumes that IEEE 32-bit format. However, the techniques that we develop can be extended to other formats, especially double precision arithmetics. So this is the sign bit. Either it's 0 or 1. P and then e to the power of e minus bias. Normalized form of a 32-bit floating point number. P is between 0 and 1. Sign bit significant, form normal or denormal. Mantissa, fractional part of the significant. E is the exponent plus 127, which is the bias. Z is the set of integers. Hold on. First, the floating point unit needs to unpack different fields from the floating point representations of A and B. Let the E field be EA and EB for A and B, respectively. Let the E feed of the result be EC. In hardware, let us use a register called E to save the exponent. In the Python notation, final value of E needs to be equal to EC. Unpacking the significant is slightly more elaborate. We should represent the significance as unsigned integers and ignore the decimal point. Moreover, we should add a leading most significant bit that can act as a signed bit. It is initially 0. For example, if a floating point number is of the form 1.0111 times 2 to the power of 10, the significand is 1.0111. We shall represent it as 010111. Note that we have added a leading 0 bit. Figure 8.16 shows an example of how the significand is unpacked and placed in the register for a normal floating point number. In the 32-bit IEEE 754 format, there are 32 bits for the mantissa, and there is either is 0 or 1. There is either a 0 or 1 before the decimal point. The significant thus requires 24 bits, and if we wish to add a leading sign, bit 0, then we need 25 bits of storage. Let us save this number in a register and call it W. Let us start out by observing that we cannot add A and a B the way we have added integers because the exponents might be different. First task is to ensure that both the exponents are the same. Without no loss of generality, let us assume that EA is more than equal to EB. This can be effected with a simple compare and swap in hardware. We can thus initialize the register E to EA. Let the significand of A and B be PA and BB respectively. Let us initially set W equal to the significand of B, with the leading 0 bit as shown. As shown in figure 8.16. To make the exponent of A and B, we need the right shift W by EA minus EB positions. Now we can proceed to add the significand of A termed as PB to W. So W is shifted EA minus AB. Then we add PA. I want to see an example. Let the significand represented by WPB PW. There is a possibility that PW might be greater than or equal to 2. In this case, the significand of the result is not in normalized form. We will thus need to shift W by 1 position and increment E by 1. This process is called normalization. There is a possibility of incrementing E by 1. That incrementing E by 1 might make it equal to 255, which is not allowed. We can signal an overflow in this case. The final result can be obtained by constructing a floating point number out of E and W and the sign of the result. So we have 1.01. So assume that the bias is 0. Okay, so in base 2, we are representing 1.01. And in base 2, we have 1.11 times 2 to the power of 1. And then times 2 to the power of 3. Assume that the bias is 0. So A is this, B is this, W is 0.01.11 significand of B. What is PB? So set W equal to Significand of B. PB with a leading bit, 0 bit. Okay, PB. Significance of A and B, BP, A and PB, respectively. All right. And this is like how many bit shifts are there, right? This 2 to the power of 3 and 2 to the power of 1. W is equal to 0, 1.11. E is 3. Wait, E is 3. E is 3. Let me see what is E again. Get the E feed of the result. C, B, E, C. E is the one on this over here is EB, right? Or EA. It's EA. Significant of B, EA. And then 3 minus 1. Zero 0.0111. W plus PA. W plus PA. This plus this. We add them normally, right? 1.1011. The C is like this. Wait, hold on, hold on. This to the power of 3. Hold on. Okay, this is what I think is happening. 1.01. 1.01. We have this number. Wait, hold on. I need to reset my tablet. In order for addition to work, we need them to have the decimal place at the same place, right? The decimal point at the same place. I'm just switching my tablet on. This will, I don't know why it's taking time. Did we assume that b would be smaller? B is the smaller one. Okay, wait. So from what I understand, I may be wrong in this. 1.01, 1.01 times 2 to the power of 3. You have 1.11 times 2 to the power of 1. This is, you're doing times 2 to the power of 3, right? But in binary, I think multiplying by 2 shifts it. So it's, this is actually, oh no. Um, Wait. 1, 2, 3. I'll just add a 0 over here. It's actually like this. This is 1, 0, 1, 1, 1, but the decimal point is here. So we are times 2 to the power of 1. Now I'll just add 0. But since the decimal point are in different positions, we can't just add all the ones and zeros normally. We can't just add them normally. Instead, we want the decimal point to be in the same place, right? So we need this in terms of 2 to the, we need this number in terms of 2 to the power of 3. I think we should take the smaller number and write it in terms of the bigger number. So this is also equal to 1, 2, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, I think it's like this. Since this and this are in the same format, since we have these two with the same decimal point in the same location, our result, we can like add the ones and zeros over here. Our result will be like this. No, not here. Yeah. So the point is that we want to add norm like with integer addition. We add we added like integer addition by putting the decimal place in the same location. Like unit to unit, tens to tens, hundreds to hundreds. And I think like we take the exponent of the larger one. This is fixed. And we set the smaller one to the exponent. We set the exponent of the smaller one to the exponent of the larger one. We write it in terms of 2 to the power of 3. Because when it's like 1 million plus 0.1, that 0.1 is insignificant, right? I think we care about the position of the larger one. But does it say here somewhere, I think? In hardware, let us use a register called E to save the exponent, the final value of A needs to be equal to EC. And let us assume EA is bigger than EB. Okay, okay. So we're assuming A has the bigger one. So similarly for this, A again has the bigger one. So if it's like this, 2, the decimal point are like not in the same place. So we need to represent this in terms of we need to represent the exponent of the smaller one in terms of the larger one. So we need to represent this as we need to represent this like this. So we have 0.1110. Then we add them. I don't know why when I explain it, like I understand it, but when I read their explanation, it confuses me. 0, 0, 1 overflow, 1 overflow, 1 overflow again. And I need to add a 0 just in case for the sign bit. 3 zeros in between. But the thing is, 2 to the power of 4. 2 to the power of 4. Hold on. So it's either in this form 1.xxx or in this form 0.xxx. Even in the previous example, they did this. Yeah, they did. So I need to represent it with a 1 at the end, 1 at the start. In example 131, let us assume that we were allowed only 2 Mantissa bits. Then there would have been a need to discard all the Mantissa bits other than the 2 most significant ones. The result would have been 1.00. To incorporate the effect of discarded bits, it might have been necessary to round the result. For example, let us consider the decimal numbers. If we wish to round 9.99 to the nearest integer, we should round it to 10. Similarly, if we wish to round 9.05 to the nearest integer, then we should round it to 9. Likewise, it is necessary to introduce rounding schemas while doing floating point operations such that the final result can properly reflect the value contained in the discarded bits. Okay. Suppose we have 2 binary. This is represented like 2 to the power of 10, and then this is represented like 2 to the power of minus 1. But when we add them, we will try to shift these bits to the right, in order to make this in terms of 2 to the power of 10. But then some of the ones and zeros would be lost at the end. So I'm guessing, okay, this is what I'm guessing. If the last discarded bit was a 1, then we do a rounding and we set this to 1 as well. If the last discarded bit was a 0, then we don't do any rounding. Let us introduce some terminology. Let us consider the sum of the significance after we have normalized the result. Let us divide the sum into two parts. P plus R times 2 to the power of minus 23, where R is less than 1. Here P hat is the significant with the temporary result in W multiplied by 2 to the power of 23. It is an integer which need to be further rounded. R is the residue that will be discarded. It is less than 1. The aim is to modify P hat appropriately to take into account the value of R. Now there are two ways in which P hat can be modified because of the rounding. Either we can leave P hat as it is, or we can increment P hat by 1. Leaving P hat as it is also known as truncation. This is because we are truncating or discarding the residue. In IEEE 754 format, the IEEE 754 format supports 4 rounding modes as shown in table 8.6. An empty entry corresponds to truncating the results. We only show the conditions in which we need to increment P hat. We give examples in decimal in the next few subsections for the ease of understanding. Exactly the same operations can be performed on binary numbers. Our aim is to round P hat plus R to an integer. There are 4 possible ways of doing this in IEEE 754 format. Conditions for incrementing the significant. Truncation, round to positive infinity, round to negative infinity, round to nearest. R is more than 0.5 or R is 0.5 and the least significant bit is 1. Truncation is the simplest rounding mode. This rounding mode simply truncates the residue. For example, the truncation-based rounding, if P hat plus R is 1.5, then we will discard 0.5. We are left with 1. Likewise, truncating minus 1.5 will give us minus 1. This is the easiest to implement in hardware with the least accurate out of the 4 methods. So rounding to positive infinity, in this rounding mode, we always round a number to the largest integer. For example, if P hat plus R is equal to 1.2, we round it to 2. P hat plus R is minus 1.2, we round it to minus 1. The idea here is to check the sign bit and the residue. If the number is positive, the residue is non-zero. Check the sign bit and the residue. If the number is positive, the residue is non-zero. Okay, if the number is positive and the residue is non-zero, then we need to increment P hat. Or alternatively, least significant bit of the significant. Otherwise, in all other cases, either R is 0 or the number is negative, it is sufficient to truncate the residue. Isn't this equivalent to the ceil function? And I think this would be equivalent to the floor function. Yeah. So now round to nearest, this rounding mode is the most complicated and it is also the most common. Most processors use this rounding mode as the default. In this case, we try to minimize the error by rounding P hat to the nearest possible value. If R is greater than 0.5, then the nearest integer is P hat plus 1. For example, we need to round 3.6 to 4 and minus 3.6 to minus 4. Similarly, if R is less than 0.5, then we need to truncate the residue. For example, we need to round 3.2 to 3 and minus 3.2 to minus 3. Special case arises when R is 0.5. In this case, we would like to round P hat to the nearest even integer. For example, we will round 3.5 to 4 and 4.5 to also 4. This is more of a convention than a profound mathematical concept. To translate this requirement, we need, in our terms, we need to take a look at the least significant bit of P hat. If it is 0, then P hat is even, and we do not need to do anything. However, if the least significant bit is 1, then P hat is odd, and we need to increment it by 1. For our discussion on rounding, it is clear that we need to maintain some state regarding the discarded bits and pay hat such that we can make the proper rounding decision. In specific, we need four pieces of information. Least significant bit p hat is least significant bit of p hat is r 0.5, is r more than 0, and it is r more than 0.5. The last three requirements can be captured with two bits, round and sticky. The round bit is the most significant bit of the residue, r. Sticky bit is a logical bit of the rest of the bits of the residue. You can thus express the different conditions of the residue as shown. Sticky bit and round bit. Sticky bit is a logical or the rest of the bits of the residue. R is greater than 0. So this is the round bit. It's the most significant bit. Um, Sticky bit is a logical OR of the rest of the bits of the residue. Hold on. Is it R always more than 0? Eh, R is between 0 and 1 included, right? We just need to check if any bit is 1. Why are we doing this? Uh, if R is equal to 0.5, we check that the most significant bit is 1, that is, and the rest of the bit is 0. Okay, that makes sense. If R is more than 0.5, we check that R is 1 and some of the bits behind in front of R, the bits less than R, they're also 1. So it's more than 0.5. Implementing routing is thus as simple as maintaining the round bit and the sticky bit, and then using table 8.6 to round the result. Maintaining the round and sticky bits requires us to simply update them on every single action of the algorithm. We can initialize these bits to 0. They need to be updated when B is shifted to the right. Then they need to be further updated when we normalize the result. Now it is possible that after rounding, the result is not normalized. The result is not in normalized form. For example, if P hat contains all ones, then incrementing it will produce 1 followed by 23 zeros, which is not in the normalized form. In case the process of rounding begins the result to a state that is not in the normalized form, then we need to re-normalize the result. Note that in this case, we need to increment the exponent by 1 and set all the matrices to all zeros. Incrementing the exponent can make it invalid, and we need to explicitly check for this case. Okay, wait. Addition of numbers with opposite signs. Now let us look at the problem of adding two floating point numbers, a and b, to produce c. They have opposite signs. Again, let us make the assumption that EA is bigger than EB. The first step is to load register W with the significand B along with the leading 0. Since the signs are different, in effect, we are subtracting the significand of B from the significand of A. Hence, we take the 2's complement of W that contains BW with the leading 0 bit. Then shift it right by EA minus EB places. I think they're describing something similar to this, but I think the wording confuses me. This value is written back to the register W. Note that the shift needs to be an arithmetic right shift here such that the value is preserved. Secondly, the order of operations is not important. We can now add the significance of A to W. If the resulting value is negative, then we need to take its 2's complement and set the sign of the result accordingly. Next, we need to normalize the result. It is possible that PW is less than 1. In this case, we need to shift W to the left till 1 is less than or equal to PW, which is less than 2. Most implementation of the floating point standard use an extra bit called the guard bit, along with the round and sticky bits. They set the most significant bit of the residue of the guard bit, the next bit to the round bit, and the OR of the rest of the bits to the sticky bits. During the process of shifting a number left, they shift the guard bit first, then shift in zeros. At the end of the algorithm, it is necessary to set the round bit equal to the guard bit and or the sticky bit with the round bit such that our original semantics is maintained. This added complexity is to optimize for the case of a left shift by one position. If we did not have the guard bit, then we needed to shift the round bit into W. We would thus lose the round bit forever. Once W is normalized and the exponent E is updated, we need to round the result as per table 8.6. This process might lead to another round of normalization. Now that we have not considered special values such as 0 in our analysis. The flowchart in figure 8.17 shows the algorithm for adding two floating point numbers. The algorithm considers 0 values also. So if A is 0, just set the result to B. If B is 0, just set the result to A. Uh, why are we doing this? Hold on. Swap A and B such that EB is less than or equal to EA. Or we may swap it, right? Store the sign here. Sign are the same. If they're not, then we do 2's complement. If W is less than 0, yes, 2's complement. S is equal to not S. Normalize W and update E. Overflow or underflow, we report. Round W, normalize W and update E. Overflow, underflow, report. Construct C out of W, E, and S. Yeah, I need to watch a video on this. The algorithm for multiplying floating point numbers is exactly the same form as the algorithm for generic addition without a few steps. Let us again try to multiply A times B to obtain the product C. Again, let us assume without loss of generality that EA is greater than or equal to EB. The flowchart for multiplication is shown in figure 8.18. We multiply them like how we multiply integers, right? We do not have to align the exponents in the case of multiplication. We initialize the algorithm as follows. We load the significant of B into register W. In this case, the width of W is equal to double the size of the operand such that the product can be accommodated. E register is initialized to EA plus EB minus bias. This is because in the case of multiplication, the exponents are added together. We subtract the bias to avoid double counting. Wait, when we are multiplying these two, we get the result 2 to the power of 4. Wait, so 1.01. When we are multiplying these two, 1.11. The product of multiplication is that we can add exponents and we can switch them around as well. So, but don't the decimal point need to be in the same position? I think before the exponent, they already are in the same position. It is the exponents that switches the decimal point. Yeah, yeah. So we multiply them like how we multiply integers. We multiply this. And then this we can add the exponent. So 3 plus 1 is 4. And whatever the multiplication goes here, that will be our final result. We subtract the bias to avoid double counting. Computing the sign of the result is trivial. After initialization, we multiply the significand of A with W and save the product in W. The product contains 46 bits after the floating point. We need to discard some bits to ensure that the final matrica is 23 bits long. Hence, it might be necessary to normalize the result by shifting it to the right or shifting it to the left. As with the case of addition, we can then proceed to round the result to contain 23 bits in the matrica and renormalize if necessary. Since there are a constant number of add operations, the time complexity is equal to the sum of the time complexity of the normal multiplication and addition. Both of them are O log n operations. Total time taken is thus O log n. If A is 0, result is 0. B is 0, result is 0. Multiply them, normalize W, update E, round W. We use XOR for the sign. So where do we add E? Oh yeah, we add it over here, right? The major difference between integer floating point division is that floating point division does not have a remainder. It only has a quotient. Let us try to divide A by B to obtain C. We initialize the algorithm by setting the W register to contain the significand BA of A. The E register is initialized as EA minus EB plus bias. This is done because in division we subtract the exponents. Hence, in their bias representation, we need to subtract EB from EA. We need to add the value back to the value of the bias back. Computing the sign of the result is also trivial in this case. Start out by dividing PA by PB. The rest of the steps are the same as multiplication. We normalize the result rounded and then renormalize if necessary. Time complexity of this operation is the same as the time complexity of restoring or non-restoring algorithms is equal to O log n. Turns out that in the case of the floating point division, we can do much better. If we are dividing them, hold on. If we are dividing them, then we can do this. No, this is 1. We can divide this separately like we do with integers, and this is 3 minus 1, which is 2. Let us try to simplify the process of division by dividing it into 2 stages. In the first stage, we compute the reciprocal of the divisor 1 over b. The next stage, we multiply and obtain the reciprocal with the dividend a. The product is equal to a divided by b. Okay, I understand. So instead of, I see we are actually multiplying it. Floating point. Floating point multiplication is an O log n time operation. Hence, let us focus on trying to compute the reciprocal of p. Let us also ignore exponents in our discussion because we just need to flip the sign of the exponent in the reciprocal. Let us only focus on the significant pb, and to keep matters simple, let us further assume that b is a floating point, is a normal floating point number. Thus, 1 pb is between 1 and 2. We can represent pb as 1 plus x, where x is less than 1. B is a floating point number, is a normal floating point number between 1 and 2. Okay, so we have 1 over pb is equal to 1 over 1 plus x. Okay, and instead of x, we write 1 minus x apostrophe, which gives us 2 minus x apostrophe half times. Wait, what? Why are we doing this? Let us thus focus on evaluating 1 over 1 minus y. Yeah, 1 plus y divided by 1 minus y square. 1 plus y, 1 plus y square, and 1 minus y to the power of 4. We keep expanding this. We end up here, and approximately we end up with this. 1 minus y to the power of 32 is very close to 1. We do not need to proceed anymore. The reason for this is as follows. Since y is less than half, y to the power of n is less than 1 divided by 2 to the power of n. The smallest mantissa that we can represent in IEEE, that 32-bit floating point notation, is 1 over 2 to the power of 23. Hence, there is no point in having terms that have an exponent greater than 23. Given that the approximate nature of floating point mathematics, this product is as close to the real value of 1 over 1 minus y as we can get. But don't we need to calculate y and y squared and y to the power of 16? It has 5 add operations that can be done in parallel. To obtain y times, okay, y multiplied by, so multiplying all the y's, we can repeatedly multiply each term with itself. For example, to get y to the power of 8, we get y to the power of 4 with y to the power of 4 and so on. Thus generating powers of y generating the powers of y takes 4 multiply operations. Lastly, we need to multiply the terms in brackets. This will require 4 multiplications. We thus require a total of 8 multiplications and 5 additions. So 1, 2, 4, 8, 16. Okay, 4 multiplications. And 5 additions. Additions can be done independently. we can multiply 1 plus y and 1 plus y square. Like we can have this operation and we can have these two. We can have these two multiplying with each other in parallel. Let us compute the time complexity for an n-bit floating point number. Let us assume that a fixed fraction of bits represents the mantissa. Thus, the number of bits required to represent the mantissa is O(n). Consequently, the number of terms of the form 1 plus y to the power of 2k that we need to consider is O log n. Total number of additions and multiplications for finding the reciprocal is also O log n. Since each addition and multiplication takes O log n time, the time complexity of finding the reciprocal of p is equal to O log n square. Hence, the rest of the operations, such as adjusting the exponents and multiplying the reciprocal with a, take O log n time. Time complexity is equal to O log n square. We observe that floating point division is asymptotically much faster than normal integer division. This is primarily because floating point mathematics is approximate, whereas integer mathematics is exact. We retain another algorithm that also takes O log n square time. We assume that we are trying to divide a by b. Let us only consider normal numbers akin to, how do you pronounce this? Akin to goal. This was this algorithm, right? So akin to the previous division, the key point of the algorithm is to find the reciprocal of the significand of b. Adjusting the exponent, computing the sign bit and multiplying the reciprocal with a are fast operations. O log n. For readability, let us designate pb as p. We wish to compute 1 over b. Let us create a function f(x) which is 1 over x minus b. F of x is 0 when x is 1 over b. Hold on, what's happening? F of x is 0 when x is 1 over b. How? Oh, yeah. 1 over 1 over b is, we are left with b. The problem of computing the reciprocal of b is thus the same as computing the root of f of x. Let us use the Newton-Raphson method. The gist of this method is shown in figure 8.19. We start with an arbitrary value of x such as x naught. We then locate the point on f of x that has x naught as its x coordinate and then draw a tangent to f of x at x naught, f of x naught. Oh, and then we do this, and then we do this, and then we get closer and closer to the root. We have this equation, and we are finding where f of x is equal to 0. We can terminate after a finite number of steps with arbitrarily small error. Let us analyze this procedure mathematically. The derivative of f of x is x naught. At x naught is minus 1 over x naught. Let the equation of the tangent be y is equal to mx plus c. The slope is equal to minus 1 over x naught square. This equation is thus y is equal to minus x over x naught square plus c. Now, we know that x naught, the value of y is 1 over x naught minus p. We thus have, we have this Hold on, what's happening? We know that at x naught, the value of y is this. Oh, we are finding the value of c, right? Version of the tangent becomes this. The line intersects the x-axis when y is equal to 0 and x is equal to x1. We thus have this as x1. Let us now define an error function of the form bx minus 1. Note that error is 0 when x is equal to 1 over b. Let us compute the error x0 and error x1. So with x0 it's b x0 minus 1. With x1 it's this. So error of x1 is the square of the error with x0, as the error gets squared with every iteration. If the starting value of the error is less than 1, then it will ultimately get arbitrarily close to 0. We can thus place bounds on the error and then we can compute the number of iterations required. We start out by observing that 1 p 1 is less than equal to p, which is less than 2, since we only consider normal floating point numbers. Let x naught be half, the range of p x naught is 1, thus minus half to 0. We can thus bound the error as minus half, which is less than or equal to this, which is less than 0. So error of x naught is between minus half and 0. Therefore, we can say the modulus is less than half. Let us now take a look at the maximum value of the error as a function of the iteration. Since we have only 23 Mantissa bits, we need not go beyond the fifth iteration. As in this case also, the number of iterations is small and bounded by a small constant. In every step, we have a multiplication and a subtraction operation. These are O log n time. Let us compute the time complexity for n bit floating point numbers. Here also we assume that a fixed fraction of bits is used to represent the mantissa, like the case of how do you pronounce this? Goldsmith division. We need O log n iteration. Each iteration takes O log n time. Thus the total complexity is O log n square. But like though the iterations themselves, so each iteration x1 is equal to 2x0 minus b x0 square. Each iteration we have a multiplication and a subtraction operation. Yeah. I mean we have one, two, three. Yeah, 3 multiplication and 1 subtraction for each iteration. These are all log n time operations. And now it's the summary. So this Newton-Raphson method also takes O log n square. Right, I will end the stream here then. What's the next chapter? Processor design. I will read this chapter in the next stream. Anyways, I will see you guys next time then. Bye.